All right, hello. My name's Ben Smith, and I'm happy for the opportunity to present all the hard work we've been doing on the Diffusion Exchange. In short, we're going to talk about a scalable, fair, and decentralized exchange. This is joint work with Alex Herman, Felix Leupold, Tom Walther, and Oliver Beige at Gnosis. So just to mention, the research area here is mainly scalable market mechanisms, batch auctions, and SNARK applications. So we'll break this down into 3 parts. First, I'll provide a motivation for the need for such a market mechanism. Then we'll talk about the details regarding the batch auction as an exchange mechanism. And then we'll get into sort of how we achieve scalability and decentralization with this mechanism as a SNARK application. For those of you who are hoping to see a lot of details about SNARKs today, there won't be that many, but just know that we're using SNARKs more for compression and verification rather than the purpose of zero knowledge. So what we see right now in current exchanges is a lot of dominant trading pairs. This is because of stable coins. A lot of these dominant trading pairs, for example, would be ETH, Bitcoin, fiat currencies, USD, Euro. However, what we expect to see once, with the rise of many stable coins is slightly less dominant trading pairs, but more of a complete graph of trading pairs. And the current mechanisms for exchange don't necessarily support a lot of trading volume when we get this kind of demand. So the token growth thesis is that we're seeing approximately 200 tokens being created per day. This little graph chart here taken from stat.blocksy.info just demonstrates the number of ERC20 tokens up until about last week. And this looks like about an average about 200 per day. So we're getting into this realm where there's a lot of trading volume between a bunch of dominant pairs, stable coins, but with the growth of token and the lower liquidity tokens, we're going to see this curve go way out here, and we're seeing a lot less trading volume. So a lot of different types of low liquidity tokens. One that we are fond of at Gnosis is prediction tokens. So Uniswap tokens, derivatives, tokenized game assets, and with this rise of tokens, we're going to need a means of exchanging them. Does anybody know how to get rid of that? I don't think that's going to do it. No? All right. So anyhow, this mechanism we're going to describe here is to aim to target some of these low liquidity tokens and make exchange a reality. So in particular, for those of you who are familiar with our prediction market platform, this project is sort of intended to be the underlying engine of exchange for prediction tokens at some point when we're ready. So just as a brief sentence here, the Diffusion project is essentially a permissionless, decentralized trading protocol that will allow anyone to add their own tokens. Or if you're familiar with the popular theme of DAOs, maybe the whitelisting of tokens would be handed over to something like that. So now we get to talk about this cool market mechanism. Anybody who's a keen mathematician will be happy to know that this is essentially modeled as a combinatorial optimization problem. And those of you who are not super mathematically inclined will be happy that we're going to start with a small example. So we're going to talk about batch auctions. And this is just an example of batch auctions for 2 token pairs. Essentially, this could actually be, this problem could be solved by hand, the optimization problem here. So what we'll do is collect orders over a predetermined amount of time. These are limit orders between 2 token pairs. Once the batch closes, we now have a collection of orders between two pairs. We could arrange and plot the orders in a way that, to get a graph sort of like this, the yellow line is orders from B to A, and token B to A, and the blue line representing orders from token A to B. The vertical length of these lines is representing the volume in an order, and it's possible that these orders are aggregated. So maybe two people submitted an order at the same limit prices, and the volume is represented there in the vertical line. Anyhow, you could sort of plot these orders together and put it in here. And what you want to optimize here is the trader's surplus. And in this picture here, the trader's surplus is the area under the curve. So essentially, with an order book between two token pairs, you could plot this, and you could determine the price between those two tokens that would maximize the trader's surplus, and settle all the orders at an optimal price. So now we're going to envision a situation where we have three tokens, and an order comes in from A to B. Another order comes in from B to C. Another order comes in from C to A. But we're still waiting on an order from in the opposite direction in order to actually. So with the traditional order book, this situation, no exchange could actually occur when you're collecting orders just between two token pairs, because no reverse order has come in yet. So while we're waiting on this, we just think, okay, let's do some sort of a ring trade, because there is sufficient demand there for some exchange to occur. So what we do here now is collect orders in a sort of multi-dimensional order book. It's one order book with all the limit orders between all the different token pairs. We've got a little cute picture here representing the order book between all the pairs there, but now we're going to envision them all in the same place. And we turn this is essentially a combinatorial optimization problem. We can no longer sketch this in a two-dimensional place and try to optimize this area under the curve. So, however, with computers and linear optimization, we can sort of plot we can determine what the trader's surplus would be for a bunch of different prices over this grid here. Executing. All right. So we'll do the same thing again that we just talked about in the example before, but now we're just going to have subtly different constraints and things like this. So now orders are collected between any token pair, and this kind of looks like a picture we've seen a little bit earlier. The order collection is still being done over a predefined amount of time. So this is the concept of a batch order collection rather than continuous order collection. So this looks a little bit scary, but essentially now what we're going to do once the batch closes is compute the uniform clearing prices. So first thing we want to do is maximize trader's surplus. Conjecturally, this is somewhat analogous to maximizing trading volume. And this is even an open problem in the research area if anybody wants to help contribute. So the constraints here are a little subtly different because we have to ensure a few things for fairness. We always need the limit orders to be respected. This was true in the two-dimensional example as well. But now that we have prices being determined between many pairs, we also need to ensure a few other things. Price coherence and arbitrage freeness. So price coherence just says that the price from one to the other is the multiplicative inverse of the price from the other back to the one. So you wouldn't be, and arbitrage freeness is actually a little bit more and implies the price coherence. Just saying that you shouldn't be able to make any money by going around any cycle in this diagram. This is, yeah, and of course the conservation of value. This says that no tokens are created or destroyed during the settlement of an auction. All of the money that goes in comes out and is exchanged. So finally, we have settlement of orders. So just reminding us, today we see dominant trading pairs where continuous order books and traditional exchanges are sufficient. But in the future, we expect to see a lot more orders between a lot more pairs, and those kinds of exchange mechanisms just won't suffice. So this is my favorite part, just talking about some of the finer details about how we implement this. How do we achieve scalability, decentralization? We've already seen how this is inherently fair. Since the solution to these optimization problems, the feasibility range implies the arbitrage freeness. So we're doing these batch auctions as a SNARK application. A few fun facts. We'll expect to have quick batch times. We can execute 1,000 orders with costs about this much. If you want to see the details of that computation, I recommend scanning that QR code and reading the formal specification. Of course, this will be a fully decentralized trading engine, and we will get into that right about now. So essentially, of course, there's a smart contract on the Ethereum blockchain. This contract sort of has, let's say, limited storage and execution, but it's sufficient to ensure the security of everyone's balances. And with that, we can say the account balances are represented as a root hash on chain. This means that the contract itself doesn't know the balance of any particular user. And transactions come in, and these transactions are sort of hashed together. The transactions come into the contract as a payload, they're hashed together, and the contract really only stores this rolling hash of information. And of course, the contract will emit events containing the relevant information to reconstruct this hash, and anyone can listen. So then what happens is that anyone can propose the state transition of all of these transactions, which have been collected over time, which is essentially the update of account balances. So you can think of it as you have a bunch of account balances. Somebody wants to deposit, somebody wants to withdraw. They're submitting deposit, withdraw requests. And limit orders are another form of request coming into here. These are all collected in a batch, hashed together, and just sort of waiting until somebody drives the contract into a new state. And this means, okay, taking the old account balances, taking all the requests that have come in over the last little while, and updating the account balances, driving the contract into a new state route representing the new account balances, and what we have is the updated set of account balances. So the security of this is enforced by a SNARK. This means there's a challenge, response, and rollback feature in place. So whenever submitting a state transition, you'll submit a bonded transition for which you could lose if your transition was proven to be incorrect. Of course, all this data is available for anyone to be able to see whether these account balances were updated correctly. And in order to resolve such a dispute, one would have to supply a SNARK proof on chain in the form of a smart contract verification. So in the event that a state transition was challenged, the proposer would have to provide a SNARK verification that it was actually correct. And in the event that they didn't, then this would roll back to the previous state. And some rewards would be obtained for doing so. So with this model, we can achieve about 25x scaling. 10 times scalability comes from the fact that the transactions are coming in as a payload, and not actually, the information of all these requests is not stored on chain. And another 2.5 comes from some other fun features we can do, such as actually submitting all of our requests as a batch of requests in a single transaction. So now, sort of just with this basic account representation in the contract state of mind, we have essentially the auction process is occurring in 3 different stages. So first we have the order collection. Any user can submit their limit orders on-chain directly or to a, say, order collection service, which would submit all of their requests or limit orders in one transaction. That's where the 2.5x scalability comes from. But of course, anyone can feel free to submit their orders individually. Once the auction batch is closed, it's time for price calculation. And this is something that anyone can do. We've described the combinatorial optimization problem. That is the sort of how are the auctions settled? What is the price calculation and how are the orders matched? Anyone can propose solutions to this thing, bonded proposals, and the contract will choose the best solution, which means the feasible solution with the highest objective value, the most trader surplus. The contract will then choose the best solution, and maybe there will be sort of a challenge period or just a little bit. Once the solution is chosen, the solution proposer will have to provide sufficient information now. They're not actually revealing their solution. They're only revealing, okay, I have a solution with this much objective value, and someone else might have, this much trader surplus. Contract will choose the right one, and upon that, the person whose solution was chosen will provide the prices that they found and the sort of fulfillment, the fractional or full fulfillment of all the limit orders that were provided. Just sufficient information to be able to update the account balances appropriately, settle the auctions. So then what we see in the settlement phase is just a state transition of account balances according to the auction results. So there are essentially 2 snarks in place here. Of course, people will need to provide snark verification in the event of a challenge for any state transition, but also they'll need, in the event that a solution is challenged, people will need to be able to provide a snark proof of feasibility of the solution they proposed. This means arbitrage free, for the most part, and conservation of value, the things we talked about as the constraints of the problem. So just to summarize a couple things, scalability here is achieved by limited but sufficient on-chain storage. The snarks are being used here for compression and security. Balances are updated in a single transaction. Also sort of the status of the project at the moment. Where are we in building? We spent a long time researching the capacity of snarks, the price of snarks, because the bigger snark in this problem here is the snark proof of the solution to the order collection. The state transition of account balances snark is a little bit smaller, but the capacity, we need a lot of capacity for the solutions. At the moment, we have sort of a core framework for a basic snap. This includes end-to-end testing, deposits, withdrawals, making sure people can submit their requests for deposits, making sure they can update the account states, and making sure that people can withdraw their funds. The limit orders and auction settlement is somewhat analogous in the sense that the limit orders are a form of a batch collected request. And of course, the state transition is already there. So we have some basic contracts as a snap base. So keep in mind, this is also something, if this seems appealing to you, the basic snark application, deposits, withdrawals, and state transitions can be used for sort of any purposes, not just a decentralized exchange. So right now, we've got account registration, token registration, deposits, and exits. Of course, there are a few services that are listening to the events in order to reconstruct the necessary information to drive the contract into its new state. So yeah, we've got a couple services ready with end-to-end tests. And so the next steps, just for us, is to sort of start to implement the order collection and challenge response rollback. And this will just be integration with the snarks themselves and ensuring that, that we can do this. So this is actually a good place to mention that we at Gnosis have an ecosystem fund. We're funding projects that integrate with our platform. We're offering desks at Full Node in Berlin, support, and I want to just go back a little bit and point out a couple places where you could probably have a good shot at contributing here. So you'll notice the order collection as a service. This is something you could do. You could build something like this, start collecting orders from people as a service, maybe charging a small fee and submitting those orders on behalf of those people to the auction. You can become a solver. Start competing for rewards and finding the best solution to these problems. Just a couple places where the Gnosis ecosystem might help get you started. So here we have just a couple places where you can look at what we're up to. The research, the formal specification is there. There's a paper on the optimization problem and how it's modeled. There's the formal specification of this as an application, Snark application. The contracts are here at DEX contracts. And some of the services, this is the event listener, the contract driver, and integration with the snarks will be found here. Just a takeaway picture, multi-dimensional order books, making use of combinatorial optimization to maximize trader surplus between limit orders for any token pair. And thanks for your attention. Here is a list of a bunch of other people who have helped contribute.
Hello? Is it on? I was just wondering what's the reason behind the challenge response rollback mechanism rather than just having to submit the snark proof like every time you propose a new state?
So first of all, thanks for mentioning rollup. I wanted to say that part of this is inspired by rollup. So I think what you're looking for here is that the snarks are expensive. And so we don't want to have to actually compute the snark proof unless absolutely necessary. So it's easy for anyone to verify that what's happening is feasible or that the state transition is accurate. As long as you're collecting the information and you have the sufficient, like essentially the state transition corresponds to what are the old balances, what are all the things that are about to change it, and then what should the new balances be. That's just essentially going through an array and then doing a couple pluses and minuses. It's easy to verify, but computing the snark for that is just much more expensive.
Does it not enforce like a liveness aspect for all the users though, to have to be like watching out if anyone's trying to steal money off them rather than just knowing that it will always work?
Right, of course. So I think also because there's some, there's some reward in place for the solvers. You can expect that maybe a solver will be sort of a contract listener. There will be somebody keeping track. I mean, and in the event that you're not actually keeping track of the whole thing, you can always replay the entire transaction history on that contract from its deployment date. We can expect that there will be, we'll at least be keeping a database of all the transactions that have gone on. And even if such a database is lost, it can just be replayed and rebuilt.
Hey, thank you.
I see one right over there.
Hey, just a question. Like, what do you now? I mean, given your kind of quite like significant depth of experience in this in constructing these kind of ZK snark sockets. What do you think are kind of some of the challenges the industry faces for like widespread adoption and development of like quite like application-specific ZK snarks to perform like large series of computations off chain?
Well, for sure, one of the challenges, I don't know about adoption, but the capacity of these snarks and the amount of information that you can actually compress and prove in a reasonable amount of time is a limitation. I don't know, you were looking for as an adoption?
Yeah, I mean, for snarks for basically, like right now you have to be quite like literate in cryptography to work with any zero knowledge system, and kind of I mean, there are a lot of barriers to entry into this industry. What do you think we can do as a community to kind of lower some of those barriers?
Well, I think maybe in the community it would be good to have a lot of easy-to-use snark frameworks. There's a lot of them out there. We've looked through many. Just maybe having something that's easy to install and easy to get up and running is a good way to ensure a little bit more adoption. At some point, you know, I know Socrates has a really nice library with a sort of very readable interface. You can construct your proofs. This doesn't require a huge amount of combinatorial literacy, but more of a sort of programming literacy. It's like how the Python language can be learned in a day or something.
Thank you.
Do you really think that having all the possible pairs helps the price discovery?
Sorry, I didn't quite catch that.
Do you really think that having all the possible pairs helps the price discovery? Because in the financial market, yes, or an assets market, we basically usually exchange against US dollar or against some common asset for a very valid reason, yes, that people tend to have a benchmark. Yeah, so if we just get into the like all the possible combinations, we lose some liquidity, and in my opinion, yes, the price discovery could be impacted negatively.
So I think you're referring to sort of this prediction that...
Yes, the price itself.
Oh, sorry, the prices?
Yeah.
Well, keep in mind that we're sort of we're working with the sort of assumption that we'll see many stable coins. So we'll see less dominant trading pairs and less of a common reference. And you know, also we may be thinking about just the exchange between certain categories of tokens, like prediction tokens. Prediction tokens don't necessarily need to have any sort of reference to some dominant pair, but maybe sort of exchanged amongst one another.
But did you make any simulations that people will be really willing to have a direct exchange between not popular tokens instead of going through a common token, like stablecoin, for example?
Well, I mean...
Do you have any simulations which will prove how this will impact the prices and the human behavior?
So, I mean, we have kind of sort of, we've kind of scraped some of we've taken advantage of some of the APIs from other exchanges, gathered, you know, I mean, these are the sort of simulations we've done with what the sort of trading looks like between these things.
Yeah, right, but all the exchanges, they don't allow to exchange, you know, any to any. There's usually you have 3 or 4 common tokens against which you exchange.
I think this is something I'm going to have to discuss with you later.
Okay.
I don't entirely understand the question. All right then. Thanks again.